Welcome to today's paper reading. Today's paper is titled, The Geometry of Categorical and Hierarchical Concepts in Large Language Models. This paper was published on the AR14 preprint by Kiho Park and colleagues from the University of Chicago. In this paper, the authors explore how semantic meaning is encoded within the representation spaces of large language models, which is a critical issue in interpretability. They address two foundational questions: how categorical concepts like mammal, bird, reptile, and fish are represented, and how hierarchical relations between these concepts, such as dog being a kind of mammal, are encoded. The authors extend the linear representation hypothesis to provide answers. They discover a straightforward structure. Simple categorical concepts are represented as simplices, hierarchically related concepts are orthogonal in a precise sense, and complex concepts are represented as polytopes constructed from direct sums of simplices, reflecting their hierarchical structure. These theoretical findings are validated using the GEMMA large language model, with representations estimated for 957 hierarchically related concepts from WordNet data. The code for this research is available on GitHub. This paper focuses on how high-level semantic concepts are encoded within the representation spaces of large language models, LLMs. Understanding this encoding is crucial for enhancing the interpretability and control of these models. The ultimate goal is to monitor and potentially manipulate the semantic behavior of LLMs by directly measuring and editing their internal vector representations. The paper addresses two fundamental questions: how categorical concepts like animal are represented, and how hierarchical relations between concepts like animal and mammal are represented. The research builds on the linear representation hypothesis, which posits that high-level concepts are linearly encoded in LLM spaces. The paper extends this hypothesis by moving from binary concept representations to vector representations, showing how semantic hierarchy is encoded geometrically, and constructing categorical variables as polytopes. These contributions provide a foundational understanding of how semantic concepts are encoded in LLM representation spaces. Figure 1 illustrates how categorical concepts in large language models are represented as simplices within the representation space. This geometric structure is crucial for understanding how these models encode semantic information. Additionally, the figure highlights that hierarchically related concepts, such as animal and mammal bird, are positioned in orthogonal subspaces, reflecting their semantic relationships. The top panel of the figure provides a conceptual overview of this structure, while the bottom panels present the actual measured representation structure within the GEMMA large language model. This empirical validation confirms the theoretical predictions and provides insights into the internal workings of these models. For more detailed information, refer to Section 5 of the paper. In this section, we introduce the foundational concepts necessary for understanding large language models, LLMs. An LLM is composed of a function lambda that transforms input text into vectors in a representation space lambda, and an unembedding layer that maps tokens to vectors in an unembedding space gamma. These components together define a sampling distribution over tokens using the softmax function. We also formalize a concept as a latent variable W that influences the model's output, emphasizing its role in affecting the output. Additionally, we discuss the concept of causal separability, where two variables can be manipulated independently. Finally, we explore the unification of the embedding and unembedding spaces through a causal inner product, which ensures that causally separable concepts are orthogonal in the transformed space. This transformation allows us to view the embedding and unembedding spaces as a single space with a Euclidean inner product, simplifying the representation of concepts. The chapter introduces binary concepts, which include binary features and binary contrasts. A binary feature indicates whether an output has a specific attribute, while a binary contrast contrasts two attribute values. Categorical concepts encompass binary concepts as a special case. The chapter then discusses hierarchical structure, where a value or concept can be subordinate to another based on attribute inclusion. For instance, dog-cat is subordinate to is_mammal. Lastly, the chapter addresses linear representations of binary concepts, emphasizing that a linear representation should modify the probability of the target concept without affecting off-target concepts. This is formalized in definition 3, ensuring that the representation is specific to the intended concept. In this section, we explore how complex concepts are represented. The high-level strategy involves representing binary features as vectors, showing how geometry encodes semantic composition, and using this to construct representations of complex concepts. Specifically, we discuss vector representations of binary features, hierarchical orthogonality, and categorical concepts as simplices. These concepts are crucial for understanding how complex ideas are structured and interpreted within the context of the research. Figure 2 demonstrates how hierarchical semantics are encoded as orthogonality in the representation space, as predicted by Theorem 6. The plots illustrate the projection of unembedding vectors on specific 2D subspaces, showing the semantic hierarchy reflected in the vector space structure. The gray points represent all 256K tokens in the vocabulary, while the colored points indicate tokens belonging to specific semantic categories. The blue and red vectors are used to span the 2D subspaces, highlighting the orthogonality that encodes the hierarchical relationships between concepts. The empirical testing of the theoretical results is conducted in the representation space of the Gemma 2B large language model. The canonical representation space is transformed to align the embedding and unembedding representations, ensuring the Euclidean inner product acts as a causal inner product. This transformation is estimated using a specific formula involving the unembedding vector of a word sampled uniformly from the vocabulary. The WordNet hierarchy is utilized to define a large collection of binary concepts, where each synset is treated as an attribute. Synsets with at least 50 words in the Gemma vocabulary are included. The vector representation for each attribute is estimated using a variant of linear discriminant analysis, LDA, which aims to minimize within-class variance and maximize between-class variance. The Lidwolf shrinkage estimator is employed due to the high dimensionality of the representation spaces compared to the number of samples. Figure 4 illustrates the existence of linear representations for binary features within the WordNet noun hierarchy. It compares the projections of test and random words onto estimated vector representations for each WordNet feature. The values of these projections are normalized by the norm of the estimated vector representation. The x-axis represents all features in the noun hierarchy, while the thick lines indicate the mean of the projections for each feature, accompanied by error bars that show the 1.96 times the standard error. This figure supports the evidence that vector representations indeed exist for these features. Figure 5 illustrates how hierarchical semantics in WordNet are encoded within the Gemma representation space, specifically showcasing the orthogonal structure predicted by Theorem 6. The figure presents three key visual elements: the adjacency matrix of the hierarchical relations between features in the noun hierarchy, left, the cosine similarity between the vector representations W for each feature, middle, and the cosine similarity between child-parent vectors parent of W for each feature, right. These features are ordered according to the hierarchy, providing a clear visual representation of the semantic relationships encoded in the vector space. In this paper, the authors aim to understand how semantic structure is encoded in the geometry of representation space. They propose representing concepts as vectors and connecting semantic hierarchy to orthogonality. This approach is supported by empirical evidence from thousands of concepts. The work is closely related to studies on linear representations in language models and theoretical efforts to understand the existence of such representations. Additionally, it connects to research on the representation geometry of natural language, particularly focusing on hyperbolic geometry. The implications of this work suggest future directions, such as refining hierarchical semantics in language models and exploring the use of sparse autoencoders for interpretability. An important open question remains regarding the geometry of internal layers in models. Thank you for watching.